Welcome to the fifth installment of the statistics portion of Math 3350 online. Last time we talked about proportion testing. So when the variable of interest is qualitative data, category data, when we just have successes and failures or proportions, we can use either the z-proportion test or chi-squared. Now this time we're going to be talking about when the variable of interest is quantitative. So we're going to be able to calculate means and standard deviations. So when we have numeric data sets, we're going to be using the t-tests and ANOVAs. So these are really powerful analytical tools. As a matter of fact, this is probably the heart of any introductory and even intermediate statistics course, is learning about how to use the t-tests and ANOVA. So William Seeley Gossett worked at the Guinness Brewery in Dublin, Ireland, and we had the z-test. We actually, in the very first brush we looked at with the central limit theorem, we looked at the idea of calculating what I called then a group z-score. And that was the idea of a hypothesis test with a z-statistic. The problem with the z-statistic is it's not robust. It's brittle. And you need large sample sizes, and you need to not be violating any assumptions to have accurate p-values. And William Seeley Gossett was working in a brewery environment, right? He was making beer, and he needed small sample sizes, right? He's doing quality assurance, and if you're doing the quality control, quality assurance, you don't want to use up all your product just on your testing, right? You'd like to use small samples. And he realized this problem with the brittle z-test, and he invented an upgrade that worked really well. Was instead of being a brittle statistic, the t-statistic is robust. And so these 1 and 2 sample comparisons of numeric data sets, we now use the t-test for. The t-test is the modern z-test. And that was William Seeley Gossett, the beer guy. Happily, beer made stats better, and stats made beer better. So the t-test is still in use today. William Seeley Gossett's work was published in the 1920s. I don't know exactly when he figured it all out, but here we are 100 years later still using the t-test, so it's very, very good. Only limitation is that it only works for 1 and 2 sample comparisons. So for example, if you wanted to compare college students in the Southeast to college students on the West Coast, right? That's 2 sample comparison, a t-test would work. But if you throw a third region in there, if you want to do the Midwest, if you want to include the Northeast, then it won't work. And we're going to need something that will allow us to do 3 or more samples. We've already met Ron Fisher. If you've been following the video series, he's the inventor of the Null Hypothesis. So he was the one who wrote down the story about the lady tasting tea. And we know from his work that how to use a null hypothesis, how to do statistical testing. And he took the t statistic and generalized it into what's called the F statistic for his last initial. And it's actually a group of tests, a group of statistical tests called ANOVA, that stands for analysis of variance. But we're just going to learn the basic one-way ANOVA, and we will calculate the F statistic. So Ron Fisher took what William Seeley Gossett had done and generalized it. So now we can do any number. Our grouping variable can have any number of groups in it. So I mentioned earlier the assumptions. Z is a brittle statistic because when we violate the assumptions and we don't have a large enough sample size, the p-values are inaccurate. So well, first we need to understand what these assumptions are. And for t-tests and ANOVA and for z-tests, we require a couple of things. First of all, the normality assumption. So the data need to be drawn at random from a normal distribution. Well, we saw in the central limit theorem discussion that a lot of things turn out to be normal when there's a sampling distribution. So we actually use the z-proportion test as actually an estimate of the binomial distribution. But still, that while it's not required, it does mess things up for small samples if we don't draw from a normal distribution. So there's an issue. And a brittle statistic like the z-statistic needs a larger sample size to overcome this. The nice thing about the t-test that William Seeley Cosset invented is that it holds up pretty well against the normality assumption as long as we have at least a moderate sample size. And if it doesn't have a large enough sample size, we still have a couple quick data checks we can do to make sure that there aren't any malignancies that will cause inaccuracies in the p-values. Now, the second assumption, independence, we can't check with statistics. It says that each data point is independent of all the other observations. The researcher needs to assure that that happens when he or she is doing the research, collecting the data. The third one is something we can check with statistics. Homogeneity of the variances just means that the standard deviations are equal. What we're saying is that for any population or subpopulation in our hypothesis, that all the standard deviations are equal. Well, it's interesting because we're checking to see if the means are different. And if the means are different, why wouldn't the standard deviations be different? So homogeneity of the variances, while it's an assumption for these tests to work correctly, it's an easy one to violate in almost every research, when we're investigating almost any research question. So those are the assumptions, and both the t-test and the f-statistic are robust. And we have some data checks that we'll go through, but they won't be that onerous. So for the normality assumption, specifically for the t-test, anytime our sample size is at least 40, we don't need any data checks at all. The t-test is so robust that the sample size needed, no matter what the underlying distribution is, as long as the sample size is at least 40, the p-values are going to be accurate. So that's great. But what if we have these small sample sizes that are less than 40? Well, for any data set less than 40, we're going to check a box plot. And it's going to be okay to use t-procedures as long as we find no outliers. Any data set, any distribution, again, we don't have to have bell-shaped yet. We just have whatever the distribution is, we just can't have any outliers. The final thing we need to be true, if we have these tiny, tiny sample sizes, so this is a really small test if we have 14 or fewer observations. But when we do, we're also going to check a histogram and look for approximate normality in the histogram. So that's a really big improvement. We have a nice robust statistic. Most of the time, sample size is 40 or more. We won't even have to do any data checks. For these moderate sample sizes, 15 to 40, we'll check a box plot, make sure there are no outliers. And then for tiny samples, yes, we're going to have to do both data checks. That's important, right? Remember that even though it says between 15 and 40, we're checking a box plot. Well, any sample size under 40, we're checking a box plot. It's just that when we get to these small sample sizes, we're checking both the box plot and the histogram. So there's two checks to do, two data checks to do for these tiny samples. So please remember that, even though this chart may not have been spelled out that way perfectly. Also, I want to mention that when we use the t procedures for a two-sample test, for independent samples, we're going to calculate this n, we're using overall sample size, right? So we use the overall sample size to figure out what to do, and then we do it to both samples, right? If we have two samples, then we'll have to do a box plot, let's say for our students in the Southeast, and a box plot for the students out West, right? So whatever I do, I use my overall sample size to figure out what to do, and for a two-sample independent samples t-test, I'm going to have to do it twice. It turns out that the t-statistic is robust, but the f-statistic was even more robust. So when we have more groups, the statistic actually becomes more stable, more accurate. And the f-statistic is almost completely resistant to inaccurate p-values. And it's so robust that as long as I have at least 20 observations total, this is across all my samples, as long as I have at least 20 total observations, no data checks are needed. And are there things we can do for tiny sample sizes in ANOVA? Heck yeah, but in an introductory class, we're just not going to run it. If we have less than 20 total observations, don't run it. And this is a good suggestion for undergraduate researchers. I mean, if you don't have 20 total observations, come on, get some more data, right? You've got a plan. If your plan is to use ANOVA, you've got a plan to get at least this. Now, in an advanced statistics class, do you have people who can analyze these tiny data sets? Yes, but for our purposes, just don't run ANOVA unless you have at least 20 total observations. So that's for the normality assumption. Remember, we could check two things, right? We can check normality and we can check homogeneity. We can't check independence. That's a research method. So for our third check, the homogeneity, what we're going to do is we're going to avoid sharply unequal group sizes. Okay, sharply unequal group sizes. So if you think about it, that's what's going to cause problems with the standard deviations. If the standard deviations aren't equal and one group is much, much bigger, then that standard deviation is going to start pulling the results off. So we want to avoid sharply unequal group sizes, which means the ratio of the largest to smallest groups is more than 2 to 1. So if I'm doing a comparison of single versus married, let's say females, and I have 15 of the single females, I can't have 40, let's say, I can't have 40 or 50 of the married women because then I'm more than 2 to 1. But if I have 15 single women in the study, then I can have up to 30 married women in the study without a problem. So as long as I avoid these sharply unequal group sizes, the homogeneity check will be fine. The homogeneity issue will be fine. One final thing, there are statistical tests that we can do to check for homogeneity. The biggest issue with them is they're not, in most cases, more accurate than the t-test and the f-statistic themselves. So while we sometimes do, in certain situations, have a homogeneity test that we can do statistically, again, it's more of a topic for an advanced statistics class. We're ready now for some examples. And we're number one, right? So the biggest cheating scandal ever for standardized educational testing occurred in, you guessed it, in Georgia. And it's interesting because we often are able to do cheat detection with statistics if you know what to look for. So one of the things that these Atlanta Public Schools employees were doing is they were changing the incorrect answers to correct answers on official score sheets. That meant erasure marks, right? So some erasure marks are just normal, right? Kids make mistakes. They put the right answer in the wrong box, realize it, have to erase. They're told to erase as completely as they can, but you know how it is. It's impossible to hide, to erase perfectly, right? So if you have to change an answer, there's going to be erasure marks. But if there are too many erasure marks, then it's not just a kid who erased a lot, right? It's evidence over several exams that there's some cheating going on, and that's what happened. So what we're going to do is we're going to figure out what the average number of erasure marks are on a paper, and then we can take a set of suspicious exams and see if the average number of erasure marks in this subpopulation, we can compare that to what the average should be in the overall non-cheating population. So suppose we have this Cheat Busters testing company, and for the entire state of Georgia, they know that the average number of erasure marks for 5th grade students is bell-shaped and has an average of 8 and a standard deviation of 3. Now I've made up these numbers based loosely on the data about what happened. But you'll get the idea of how they caught these cheaters and why the evidence was so powerful against them. So let's just suppose they had 117 5th graders in this school that was suspected of cheating. And so instead of the 8 erasure marks. Let's just suppose there's just a tiny difference here, right? Now we have a group in this school where the average number of erasure marks is 9.5, and they have a slightly different standard deviation. And the question is, do we have evidence of cheating? So this is a sort of prototypical one sample t-test, right? What am I doing? I'm comparing a subpopulation, which in this case is the fifth graders at this school, to an overall population. Here, the overall population is, erasure marks, average erasure marks for these fifth graders all across the state. So I'm comparing the fifth graders in the subpopulation to the fifth graders in the overall population. So we're going to set up the null hypothesis to compare these averages, right? So mu sub 0 is the symbol we use for the overall population average. And then when we write mu, we're going to mean the subpopulation average. Right? Now, we've been dancing around how to set alpha, and we have set it slightly differently recently. And so here we're going to test at the alpha equals 0.001 level. Why? We're using a much lower level of alpha than 0.05 because we want to be very sure. We're going to make this accusation in court. We're going to potentially send people to jail, and they did go to jail. So we're going to use a much more strict alpha. So this is a t-test, a one-sample t-test. And by the way, when I am doing a one-sample t-test, I just refer to it as a t-test. If I'm doing something other than a one-sample t-test, I specify. And here's what I was talking about with the symbols. We're using this mu to indicate the subpopulation, the fifth graders from the school that where the suspicious test came from. And then mu sub 0, right, is the number that goes in the hypothesis. So the 8 is the mu sub 0, and we're comparing the mu, the average from the subpopulation, to the overall population average of 8. And our question is whether or not our null hypothesis is saying, suppose that we had 117 exams drawn from this statewide normal population where the average is 8. What's the probability that we'd see the data, right? What data? This data from the subpopulation. What's the probability we'd see this data in the subpopulation if it was actually drawn from the statewide data? And verification, we are fine. We have a large sample size, well over 40, and there's no problem with the robustness of T. We'll take care of we'll have accurate p-values. When we run the test at the I'll have to fix this. Sorry, guys. Run this test at the 0.001 level. Let me show you how that works on the graphing calculator. So we're going to go to Stat, Tests, and this is the one sample t-test. And all we have to do is put in the statewide population values. T-test. The average is 8. That's all I need. I put in the 8. And then I put in my sample statistics, which were 9.5 for the mean and 4 for the standard deviation, and then we had 117 exams. I think that's right. Isn't that what we had? Yes, 117. I'm sorry, I just had to go back and check. So here we are running the test. Let me get my graphing calculator back up here. 117 is correct. We are testing the greater than. So this line here is the alternative hypothesis. We just set it up to match the alternative hypothesis, and that's correct. Greater than is correct. So I can come down here. I can hit calculate. I prefer to hit draw. I like to see the bell-shaped distribution. So this draws, the t-distribution is a bell-shaped distribution. And this shows me the bell-shaped distribution. It's going to draw a vertical line. And oh, here we go. It's actually, the vertical line is so far over here. that we're not even able to see it. So you can see the t-statistic is showing us that this group of scores is more than 4 standard deviations away from the state average as a group. So we've calculated a group t-score, a t-score for the group, and it's more than 4 adjusted standard deviations away from the mean, where we take that sigma over the square root of n, or in this case s over the square root of n. So it's more than 4 corrected standard deviations away. It's giving us a p-value of 0. If you come back in, whenever you get a p-value that's so low it's rounded to 0, you can come back in and hit calculate instead of draw, and it will give you an answer switching over to scientific notation. And here you go. There is the p-value that is much less than alpha. Sorry again about this. And since p is far less than alpha, we reject the null. And we have very strong evidence that there was cheating going on. So there are 2 different ways to do a multi-group t-test. And I've set up a single example that's going to branch either direction. So think about testing a cold medicine, and suppose that we have pilots who are flying, and the question is whether or not, we know that many cold medications make us drowsy. Does the drowsiness actually affect the pilots enough in the cockpit that they wouldn't be safe if they needed to use it while they were flying? So the researchers are going to develop a series of critical tasks. They're going to time the pilot. The pilot sees a warning indicator and has to quickly go through the response steps, right? And the researchers time how long it takes them to work through the correct emergency protocols. Okay, so there's 2 ways to approach this. So we can compare the average critical response times of 20 unmedicated pilots to 20 medicated pilots. Right, so here we have a treatment group and a control group, right? The control group is the 20 unmedicated pilots, and the treatment group is the 20 that are taking the treatment, that are testing the cold medication, right? So that's treatment versus control. The second way we could do this is we can have the same pilots test with, well, they do the simulation twice. Once they do it with the medication and once without. Now, when we do this, we have 20 pilots. What we'd normally do is we'd randomly assign them to going first. Half the group would go with medication first, and half the group would go unmedicated first. But that's a research design question. So let's just suppose, oh, and by the way, we call this pre-test, post-test, right? It's not quite that way, the way I described it, but this is the idea that when we have pre-test data versus post-test data, we can use what's called a matched pairs t-test. So this pre versus post is an important research design that we can use a t-test for. Let's take a look at both of these. I'm not going to go through all the calculations. I go through them elsewhere in the learning materials. But here's the treatment versus control. And we have the values here. So the control group, right, had an average of 6, 2-second standard deviation. There are 20 of them. The treatment group, they're a little bit slower, right? Because their number of seconds is higher, that means they were moving a little slower. So we're going to test for a difference at the 0.05 level. Should we be testing at a lower alpha because, we're going to approve this for airline pilot use? Probably, but let's go with it. We can talk about, there are good reasons to set alpha differently than 0.05, and this might be one of those good cases. You could argue that. And we will argue those kinds of situations when we get to when we get a couple more units into this course. So the procedure we're running is what's called an independent samples t-test. Independent because there are 20 different pilots in the control group than there are in the treatment group. Nobody from the treatment group can be in the control group and vice versa. The samples have to be independent. So here's our setup. Now we have these symbols. The mu sub t is the average response time in the treatment group, and mu sub c is the average response time in the control group. And the concern we have, so this is what we're testing. We hope not to reject the null if we want these pilots to be able to use the medicine. But if we reject the null, we're going to be saying that there's evidence that the treatment group is higher. Remember, higher, more number of seconds. They're slower. So if mu sub t is greater than mu sub c, then these pilots are significantly slower on critical tasks when they're taking the medicine. So verification, n is exactly 40, so we don't have to do the data checks. When we run this test at the 0.05 level, we calculate a p-value that is just slightly less than alpha. And since p is less than alpha, we are going to reject the null. And the research conclusion, the evidence suggests that this cold medication has a significant negative impact on the pilot's performance. Let's take a look at this in the pre-test, post-test design. So now we have just 20 pilots, just 20. And that's important. Remember, before we had 40 pilots, now we have 20. And the researchers are going to do this test, and they're going to calculate what's called a gain score. So they don't really care what they make on either of the tests. What they care about is the difference. And a lot of people talk about these different scores. I think of them as gain scores because generally speaking, gain is post minus pre. We can test for negative gains. Just because we're calling it a gain doesn't mean it went up, right? If we're talking about a group of people with, say, hypertension, high blood pressure, we'd actually want a negative gain if they're improving. So I actually use a mu sub g to talk about the average gain. Okay, and here what we're concerned about, again, is number of seconds. We're talking about, so this gain score is being calculated. So gain, right, is going to be not post minus pre, it's going to be treatment minus control. So I'll just do T minus C. I do not have good control of the mouse in this particular setup, so my handwriting is going to be terrible. So the gain scores are equal to what their scores under the treatment were minus their control group scores, right? Their scores when they did this without medication. So their gain is going to be an increase in the number of seconds it takes them to do these critical tasks when they're taking the medication. So what we're concerned about is whether or not the gain goes up. So this should be a less than. Sorry, I'm locking up because of this symbol here. I'll have to fix that in the notes, right? Since n is less than 40, we only have 20, but we do have more than 15. We don't have to do a histogram, but we do have to check that there are no outliers in the gain score data list. And I don't have the data, so we're going to assume that we had access to this data and we did a box plot. And the box plot is showing no outliers for these 20 gain scores. Okay, well, if that was true, then we can run this as a one sample t-test, and that's important to note that this is a one sample t-test on the gain scores. So we don't have 40 observations, 20 pre, 20 post. We have 20 total observations, 20 gain scores. So we do our verification on the 20 gain scores, and we're going to run this as a one sample t-test on the gain scores. Notice what happens though. Look at these p-values. So even though we only have 20 pilots now instead of 40, we're using a more sensitive test. This matched pairs dependent samples t-test. Oh, and by the way, I used matched pairs in the other materials. I probably should have used it here. So I'm not even going to try to write that. But matched pairs or dependent samples t-tests are very sensitive. They're good at picking up the actual differences in gains rather than the treatment versus control design where the two sample t-test is picking up a lot of noise, a lot of individual differences between the pilots. Here, we're just zeroing in on the differences in the gains, and it makes it a much more sensitive test, and instead of just barely having double the sample size and just barely sneaking in under 0.05, here the p-value is much, much smaller. We would have rejected at the 0.01 level. So this is much stronger evidence. Why? Because the matched pairs t-test is a much more sensitive design. Since p is less than alpha, we reject the null, and now we have really strong evidence that this cold begone has a significant negative impact on the pilot's performance. Lots of situations have more than two groups. So there are three different t-tests: the one sample t-test, the two sample t-test, and the matched pairs t-test. And they're all good. Even though the test was invented 100 years ago, William Seeley Gossett, the beer guy, did a great job. They're good, robust, modern statistical tests. The big problem is, what do we do if we have more than two groups? If our grouping variable includes more than just two groups? So one situation might be that we're testing this, a couple of cold remedies amongst the pilots, right? And we have cold begone, and we have some other treatment control treatment group, and then we have a control group. And this is interesting. I just threw this in. Your mom really was right when she said if you have a cold to drink lots of juice and water, right, to hydrate. It turns out that water, H2O, is a really good expectorant, right? It does help us clear out those cold and flu season symptoms pretty well. So we don't just need a treatment that's better than somebody doing nothing. We need a treatment that's better than just drinking lots of fluids. But this is four groups, and if you were doing a design like this, t-test is simply not going to work. And in that case, we're going to use ANOVA, and ANOVA is the generalization of the t-test. That's what Fisher was intending, that we're going to take what Gossett did, and Fisher was going to improve it, make it more useful in more situations. And I skipped over this. I would like to talk about it, but it's probably going to be in a different lesson. So ANOVA controls overall alpha. So could we take a look at comparing pairwise treatment 1 versus treatment 2, then treatment 1 versus control? The problem is we end up with 6 tests, and each of these statistical tests have some amount of error because they're based on probability models. And the error starts to grow out of control if I do multiple t-tests. So the one huge advantage of ANOVA is that you get to set your alpha, you get to set your level of significance, and then all of the testing, including the checking for pairwise differences in the post hoc test, which you'll see in a moment, all of that is done, and the overall alpha doesn't grow out of control like it would with multiple t-tests. So let's take a look at this example. I found this in a statistics book. It was a report of real research, and I was appalled. So they split these fourth graders. Okay, so fourth graders, what are they? They're 9 or 10-year-olds, 9-year-olds, 10-year-olds, right? And so, okay, pattern recognition task. But in group 1, the child was praised for correct responses. Group 2, check this out. In group 2, these 9-year-olds, these 10-year-olds are criticized by an adult for incorrect responses. They get it wrong, they get yelled at. In group 3, the researcher stood nearby and showed interest in the child's progress. Sorry, that should be, missed my punctuation there. And in group 4, the researcher watched silently from another room through a one-way mirror, and the children's success on the task was recorded. Okay, so let's talk about a little bit of research ethics, right? I mean, these are kids who are probably damaged. They probably have to talk to a therapist when they become adults because they were traumatized in this research, where somebody criticizes them for getting something wrong in a research setting. So just want to say that we do have ethical obligations as researchers with human subjects, and there are protected classes like minors, like pregnant women, right? We have to be very careful if there might be any damages. And those who are mentally ill, we have a responsibility to make sure that they can understand and participate of their own free will in in these kind of research situations, right? So they must have done a lot with these parents to get authorization to randomly select people into the criticized group. But anyway, so yes, there's some ethical problems with what it is we're doing, and I don't know what the researchers did or what they were trying to accomplish. But here's our research setting, and you can see the averages. So look, when they actually give the kid a pat on the back, have a nice high average, show a little interest, you still get some good performance out of these kids. You just leave them alone, they do okay, and then look at the criticism average. The average out of the criticism group, I mean, these kids are really not doing well, right? So notice that we have some different standard deviations. You can see the sample sizes here. And by the way, I've given you enough information. You can go online and just type in ANOVA and get a little web app that will run this for you, and you're perfectly welcome to do that. The procedure is ANOVA. The null hypothesis is that every single one of these averages came from a sample that was, the null hypothesis is that they were all drawn from the same distribution. Okay, well, it's possible, right? It's possible that these values, even though the ones I'm highlighting here, they look a little suspicious, right? It's possible that they were randomly drawn from the same identical distribution that the other samples were drawn from, and we just ended up with some low values there. That's possible. That's what the p-value is going to tell us, the likelihood that the null hypothesis is true. The alternative hypothesis is that at least one of these groups is significantly different than the others. All right. So we do have our sample size met, right? We have 9 plus 11, right? So we have exactly 20. That was on purpose. We have exactly 20. So the robustness of the F statistic will guarantee accuracy of these p-values. Again, if you want to go online and run this, it's really easy to do so. You'll end up with a p-value of 0.05 when you run this test, and therefore we would reject the null. It's lower than the default alpha of 0.05. And our research conclusion is that evidence suggests that there was differential performance, right? The null hypothesis was that all of these groups, all of these samples were drawn from identical distributions, right? But evidence suggests that's not true. So what seems likely? Well, it seems like the performance was different in different groups. Now, an ANOVA is not done just when you finish rejecting the null or failing to reject the null. In the instances where we reject the null, we need to perform what's called a post hoc test. And I didn't go through that. I did put this little note in here that I am shocked to find out there was evidence that the performance differed between groups. But in the flipped classroom worksheets, where you'll go through the computations, plus there's a whole example that's worked out in detail by hand showing all the steps. You'll see how to do these post hoc tests. It's called a Tukey HSD. HSD stands for honestly significant difference, and the RStudio dynamic course notes do go through that in detail in several examples. So you'll see how to do the post hoc testing. But here's the big idea. With ANOVA, if we reject the null, we have to do post hoc testing to figure out where the differences are. I'll tell you where the differences will be when we do post hoc testing on this guy. They'll be right there in the criticism group, right? And the criticism group seems lower than the others, especially the praise. So, but the Tukey HSD post hoc test will give us strong evidence for exactly where the pairwise differences are. So there you have it. There's a brief overview of our T-test and ANOVA. Make sure you go through the flipped classroom worksheets and the RStudio dynamic notes.